Let's discuss graph theory. So graph theory is very important topic for computer science students. Why? Just think about it. Why we have to study about graphs? We are computer science engineers, right? Then why we require this mathematical concept? The reason is graph is a model. Okay, so we can use that model to represent real world problems. Generally, so this is the idea. We have problems, and whenever that problems are represented in a model, we can understand them clearly. That's why we use models. Okay, so using the model we represent a problem, and when you have a good model for a problem, then we can understand that problem by the properties of models. Okay, every model will have properties. Okay, so model or let's say structure. So I can say a structure. So structure can be used as a model. When you use a structure as a model, then probably the properties of structure can be used to understand that problem. So then we solve it very easily. That is what the idea. Example of such structures are lattice, maybe set, anything. Otherwise relation, all these things already we have studied. That's why discrete math is also known as discrete structures. So we are going to study a lot of structures. Already we have studied what is set, what is relation, what is lattice, right? Now similarly graph. So this graph is going to be a good structure for so many problems. That's why we have to study about graphs. When you study graph structure, you will be studying, properties of graphs. Once you are, quite familiar with all the properties of graph, then when you have a real world problem, then simply convert into graph structure, and using the properties of graphs very effectively you can solve the problems. That is what we are going to do. Understand? Now, let's begin with variations of graphs. Okay, so your graph can be classified into two parts. One is directed graph, second one undirected graph. Before that, what is graph? How can I formally define it? So any graph is formally ordered pair where V is simply set of vertices or points. So how to understand vertices is, let's say they are all objects. Okay, now E equal to set of edges. So how to understand edge is? Edge is a relationship among objects. That's it. Okay, we have objects and relationships. So V comma E. So let's see the variations of such kind of V comma E. Directed graph, undirected graph. First I will draw a graph which is directed graph. After that we'll see formal definition of directed graph. So example, this is my real world problem. There are three boxes and they are playing a game. Okay. And that game, first of all, one particular game is conducted between A comma B. That means it's a relation, right? Boxes are objects, and now there is a relation called match, right? So one match is held between A comma B. Then A won the match. See, understand it. So because there is a match, there is a relationship. That's why an edge. This is actually an edge. These are all objects. Now why direction? Think about it. Because between match A comma B, A won the match. Similarly between B comma C, if B wins the match, and between A comma C, let's say A wins the match, then you get this kind of structure. This is nothing but graph, because graph is set of objects and set of relationships. Usually in pictorial form we represent relation as like this, and I mean an edge. This is called an edge, of course. Using the edge we do it, and we put an arrow. Whenever we keep arrows, sometimes we require it, depends on the real world problem, then that graph will become directed graph. Understand? Now sometimes you don't require you know these arrows. Think about the reasons, like any application or any real world problem you are seeing. Yes, I will show some problems which are not required these edges, directions especially. Example, let's say there are four people A B C D, and I would like to represent a relation called brothers, like. So A and C are brothers. So it is not like A to C is a brother. Okay. So it's like A and C are brothers, and let's say C comma D are brothers, and B comma D are brothers in that way. Okay. So then probably I use undirected graph. Here directions are not important. Understand? Now one more example, let's say cities. There are four cities, let's say. Consider the small example C1, C2, C3, C4, and I would like to represent the roads between these cities. Then between C1 comma C2 I will draw a road, but direction I don't draw. The reason, whenever there is a road from C1 to C2, then there is also a road from C to C1. So the people who stay in cities probably have this doubt. What about one ways? Then that will become directed graph. Okay. So in cities you will have directed graphs. Okay, to represent the roads of cities. Now to represent roads of villages, like example C1, C2, C3, C4, less congested roads, then definitely that people of village doesn't require edges, I mean directions to the edges, right? Then you will get undirected graphs. So there are two kinds of graphs, directed graphs, undirected graphs, and we need both of them. Depends on the real world problem. So we covered what is directed graph, what is undirected graph. Let's try to give the formal definition of directed graph, undirected graph. To get the formal definition, we know that graph is v comma e, isn't it? So already it is defined, but let me clearly define. There is a difference between these two graphs. We know that with respect to edge form. So try to write edge set here. What is edge set here? It can be written as, you see, it is an element here. I want to represent this edge. So A comma C, I write like this. Then C comma D, right? And then B comma D. AC, CV, BD. So why I am writing two elements? Because the relationship is among two elements. Why I am writing, in set form? The reason, order doesn't matter. That's it. That's why. Now the edges of undirected graph is nothing but they are all sets of two elements. Okay, the two elements may not be different. You can also have this kind of an element like A comma A. I can repeat a object two times, then probably that would become like this, right? A to A. This is called self loop. Okay, self loop is a special edge which is from element vertex to itself, right? So this is about edges of undirected graph. Let's see the edges of directed graph. So let me show that. First we write the edge form E. Now to represent this edge C1 to C2, direction is important. So in mathematics we use a structure called ordered pair, right? C1 comma C2, then probably C2 comma C3, then C3 comma C4, then C4 comma C1. So here there are four elements in this edge set. So now the directed graph edges are nothing but they are elements where each element is in the form of ordered pair. That's it. Okay. If it is set of ordered pairs, it is directed graph. If it is set of sets and set of sets of two elements, then that will become undirected graph. Okay. So in that way we can formally define directed graphs and undirected graphs. Here simply mention that E equal to set of edges where set of edges, of course, set of edges where each edge is ordered pair. Okay, let me write ordered pair. So this is the concept of directed graph. So here E equal to set of edges, same thing like this, set of edges where each edge is simply set of two elements, set of two elements. So that two elements might not be distinct. So this is the formal definition of directed graph, undirected graph. Okay. Now there is one more variation, that is simple graphs, multigraphs. Your graphs can be again, classified into two parts. It's a different classification. Simple graphs, multigraphs. Let's see them. Simple graph is a graph without self loops, comma parallel edges. So I will define what is self loop and parallel edges. Remember that simple graph cannot contain the self loop and parallel edges. Example, what is self loop is an edge from A to A, you might know it. Second one, parallel edge is nothing but an edge which is repeated multiple times. See like this. So between A comma B, if you have multiple edges, then we say that they are parallel. So how to write them? In set form you write like this, right? An edge A comma B, A comma B, A comma B. I can say that all these edges doesn't have any own identity, right? So how can you differentiate this A comma B, this A comma B, this A comma B? So such kind of edges are called parallel edges or multiple edges. Okay. Now, multigraph is a graph which does not contain, parallel edges. Okay. So, but what about self loops? The question is, does multigraph contain self loops? So it is ambiguity. So it is ambiguously defined in theory. So some people say that multigraphs contain self loops. Some people say that multigraphs does not contain self loops, and there is one more group. That group doesn't say anything. Like they neither allow nor disallow. So this is a story about multigraphs. So what I do is, so I just I don't say anything about self loops. You might have, might not have. Okay, so we don't talk about them. So because it is ambiguity, so probably it depends on the discussion. Like if you want to allow it, that's you can allow. Otherwise not. So what I do is I don't say anything about it. That means still I may allow, right? That means in a graph, I don't bother whether that graph contains self loop or not. But what I worry is whether multiple edges are repeated or not. Okay, example this graph. For me this is multi-graph because parallel edges are allowed. Okay, don't bother about whether there is a self loop or not. This is not a simple graph. Understand? So in that way you can understand simple graphs and multi-graphs. Okay. Now let's see some properties of graphs. First one is degree of a vertex. We are going to use this degree of a vertex so many times. Let's begin with undirected graph. In undirected graph, what is degree is, let me focus on one vertex u. Okay. So see, degree of u is 4. It's a number, integer. And by seeing this number, you can easily understand that number indicates the number of edges which are associated to it, right? So according to the definition of degree, so degree is a number of edges which are incident on a vertex. In undirected graph, I can define degree as number of edges incident on that vertex. Okay. Now, when it comes to directed graph, so there is no such degree concept. We have two concepts here. One is in degree, second one out degree. Okay. So I will tell you what is in degree and out degree. Example, in directed graph you will have directions, right? Consider this vertex. Okay. So two edges are coming inside, one edge is going out. Then whatever is coming inside is called in degree. So we usually denote it by plus positive, and out degree we usually denote by negative. So write a vertex number, let's say u, and d of u is usually degree, but there is no simple degree here. We have in degree, out degree. That's why d plus of u, d minus of u. In this problem, d plus of u is nothing but number of edges which are incident towards u, incoming. Okay, so number of edges incident towards, so that would be how many? 2, right? Okay, number of edges which are incident from u is nothing but out degree. Here out degree is 1. In that way we can define in degree and out degree of any vertex. When it comes to undirected graph, there is only one degree. Okay, that degree, especially d of u in this problem, is 4. So this is about degree concept. Okay. Now what about self loop? When there is a self loop, how to understand it? According to the definition, number of edges which are incident on this vertex, right? So what we can imagine, so see, the same edge is incidenting from two sides, right? From this side. So I can say that this point has, two incidenting places, right? Otherwise, so two same edges incidenting here and here. Then I can count it as 2. So degree of A is 2 here. Otherwise it's an exception. Okay, there are two things, either you can reason like this, that's why degree of a2. Second one, so I will be going to teach you sum of the degrees theorem. In sum of the degrees theorem, so degree of this kind of vertex should be 2, then only theorem works. Otherwise it won't work. For every other than self loops, for every graph it works, but for self loops, if I take degree as 2, then only sum of the degrees theorem works. Okay, in that way, that's the reason, so people count this edge twice. Actually, edge wise it is only 1. Okay, but in degree calculation, they take it as 2. So this is called an exception. If you take this as exception, then in sum of the degrees theorem, so you get advantage. That means we can say that sum of the degrees theorem is true for every graph. Okay, I'm going to teach you sum of the degrees theorem, and that sum of the degrees theorem, if you take this vertex degree as 2, then only it will be true. So why I should make sum of the degrees theorem true, I will tell you. So let's say there are 100 graphs, let's say out of 100 or 100 percentage, 95% of the graph generally does not contain self loops, right? Only 5% of the graphs I can say contain self loops, maybe less than that. Okay, that means I want to say that a graphs with self loops are very rare. Let's take some very rare means 1%, and 99% graphs doesn't contain the self loops. Then in these graphs, so there is a theorem called sum of the degrees theorem. It always works. Okay, that I'm going to teach. What is that sum of the degrees theorem? Don't worry. So, but if I count this degree of A as 1, since there is only one edge which is incidenting, then sum of the degrees theorem fails. Only reason this 1%. Now you decide. If I take this degree as 2, then sum of the degrees theorem works for every graph. So that's why the authors who studied graphs first, they realized that, and they thought that degree of A, let's make it 2, so that sum of the degrees theorem can be studied without any exceptions. Like otherwise what happens, you have to study of the sum of the degrees theorem like this. Sum of the degrees theorem is true for all the graphs except this kind of graphs, right? It will be complicated. So if you put this exception, then we can easily say that every graph satisfies sum of the degrees theorem. Okay, I have analogy here. Generally 99% of the Indians are good, isn't it? Only 1% are bad. Okay, then for outside people, like let's say for outside world, India is a good country, but still they say that we are good, though there are 1% of the people who are bad. But based on just this 1% are very, otherwise some 0.1%, based on that we should not say that India is a bad country, isn't it? So that's why what we do is we assume that, let's say these are also good, and we can justify that, and we can generalize it to like Indians are all good. For that we have to take this exception, though we have the other some bad people, still we should say that Indians are good, so that we are generalizing the majority, right? In the same way, so here if I take degree of a 2, actually it's an exception, but most of the students will have this question that degree of a should be 1, but the only thing why we are making degree of a 2 rather than 1 is there are a lot of theorems. If I take degree of a 2, then that will be that will work. Otherwise I can say this kind of generalized statements like majority of the graphs satisfy some property. For that we have to take degree of a 2. Understand? So treat this as an exception. Let's take some graphs and compute degrees of vertices. Okay, let's take this graph. degree of C, number of edges incident on this vertex, 1, 2, 3, 4, right? So each parallel edge to be counted once because these are all separate edges. Now degree of B, so number of edges which are incident on this vertex, 2, okay. Now degree of D, see 1, 2, 3, 4, 4 edges are incident on D. Apart from that, self loop. Self loop is counted twice, right? That's why 4 plus 2, 6. So degree of A, 2 as usual. Okay. So this is about calculations in this one. Let's see this one. Let's begin with C. So number of, first of all, I am going to incoming degree. So 1, 2, see the self loop. The self loop is coming towards our vertex C, isn't it? So that's why 1 plus 2, 3. Now D minus of C, number of outgoing edges. Is there any edge which is going out? So definitely these two are incoming, not outgoing. So this third one you see. If you watch from here, definitely you understand that this edge is going outside. Of course coming inside, but at the same time I can treat like it is going outside, right? So we can count it in incoming and outgoing. So that's why degree of C 1. Okay. So I'm taking this one as outgoing edge. So if you want to get clarified, watch from here. Then it is going from out. It's going out, right? Now come to D plus of B and D minus of B. Number of incoming edges for B, 1 is incoming, right? Number of outgoing, 1. So D plus of A. So 1 is outgoing, 1 is incoming. That's why 1 and 1. In that way we can calculate, sorry, 2 are outgoing, right? So that's why incoming is 0 and outgoing is 2, right? See, outgoing and outgoing, no incoming. Understand? Now this is about calculations of degrees. Now we'll see some important theorem in graph theory, that is sum of the degrees theorem. So sum of the degrees theorem we can apply for every graph. Okay. So we'll see first sum of the degrees theorem for undirected graphs. After that, we'll see sum of the degrees theorem for directed graph. Let's begin with undirected graphs. So according to sum of the degrees theorem, the statement is sum of every degree, if I do, then you get twice the number of edges. So from now onwards I use this notation. Mod V means number of vertices anywhere and mod E means number of edges. Okay. Now, so 2 into mod E. Here E is nothing but edge set and mod E is number of edges. So why sum of the degrees should be twice number of edges? We'll see. I will show one graph and I'll try to count sum of the degrees. So meanwhile you can understand that why it is twice the number of edges. Let's take self loop. Okay. Now what I do is, whenever I do degree counting, then I mark the edge, because we know that counting the degree is nothing but counting the edges, right? So degree of A. Let's come to degree of A later. So degree of D first. Number of edges which are incident on D, let me mark it 1, 1, right? Since each edge is incident on 2 vertices, you see, other than self loop, every edge is incident on 2 vertices, then that edge will be counted twice. You will understand this later. Degree of C. So number of edges which are incident on this vertex C is this one, this one. See, this edge is counted twice because D counted it, C counted it. So degree of D2, and that we are counting this edge, and in degree of C we are counting this edge again, right? Since that's why every edge is counted twice. When every edge is counted twice, then what happens? This happens. You get 2 into E. Let's see degree of B. This one, this one. That 2 indicates this one and this one, isn't it? Now every edge is again counted twice, but this edge is not counted twice. Why? Because I have not calculated degree of A. Let's come to degree of A. 1, 2, right? Apart from self loop. If there is no self loop, then every edge is counted twice. Now, though this edge is only 1, then it is only incident on one vertex, we know that. If you don't count it twice, though it is one edge, then what happens? Sum of the degrees theorem will fail only because of self loops. That's why they put an exception. That exception is loop should be counted twice in the degree calculation. Then degree of A will become 2, 3 and 4, isn't it? Yes. 2 plus 2, 4. Now you see 4 plus 2, 6, 6 plus 2, 8, 8 plus 2, 10. So 10 equal to twice the number of edges. So we using that we can compute the number of edges, which are nothing but 5, isn't it? 1, 2, 3, 4, 5. Yes. So because of this process you understand sum of the degrees theorem, correct? So from now onwards remember sum of the degrees if I do for any undirected graph, always you end up with twice the number of edges. So it is not only for simple graphs, you can use it for multi graphs too. Okay, that means I can allow multiple edges here, still you get sum of the degrees theorem correct. Understand? Let's see sum of the degrees theorem for directed graphs. Okay, for that let me take a vertex u and let me randomly draw some of the incoming and outgoing edges. Okay, now you see whenever I do d plus of u, that means incoming degrees if I take the number of edges which are incoming 1, 2, 3. Question number 1, is this incoming edge is incoming for any other vertex? Definitely no, right? So because it is incoming for, it can be incoming for only one vertex, then this one, this is definitely not incoming for you, then definitely it will be for some other vertex, isn't it? So what I realized is when you have an edge, every edge is going to be incoming for some vertex and outgoing for some vertex. You should understand that. Then if I count incoming edges, since every edge is incoming for only one vertex, then if I do d plus u for every vertex, then every edge will be counted exactly once. The reason, each edge is incoming for exactly one vertex. So then if I compute incoming degrees of all the vertices, every edge will come into the picture, isn't it? No edge can miss. Why? Whatever the edge you take, that should contribute to incoming of, that will be incoming of some vertex, then definitely it will be contributed appropriately. But no edge is counted twice. Example, let's say I am counting one edge twice, then this should happen, right? Example, I am counting one edge in incoming of, example, let's say I am counting this edge in 1 in degree. I am also counting same edge in another vertex calculation. Then example, this is vertex A. Then there is again vertex B and this edge name is E. What if this edge is going to be incoming of another vertex? Imagine, will it happen? If it happens, then one edge, try to draw this kind of edge which is incident on vertex A, vertex B at a time. It is impossible. When it is impossible, then every edge is definitely should be incoming of only one vertex. Then if you do sum of the all that incoming degrees, then what is in degree? Degree is nothing but counting the edges. What is sum of the incoming degrees? So sum of the degrees is nothing but counting all the incoming edges of every vertex. Since every edge is incoming for only one vertex, you are counting only once, then you get mod u, right? Similarly, so I can prove for out degree. Understand? So this is about sum of the in degrees and sum of the out degrees. Okay. Now when it comes to self loop, still we are right, because this self loop is incoming for one vertex, outgoing for one vertex. That's why this self loop is counted exactly once in degree once, out degree once. Understand? So that's why every edge is counted exactly once.